It's my pleasure to be with you, virtually with you, for the second year. I hope next year we could do it in person. And yeah, you already introduced me, but indeed, I started my young career as a software engineer at Databricks, leading their Spark infrastructure team. Then I co-founded Data Mechanics. And in June of this year, we were acquired by Spot.io. And so I'm now a product manager. Basically, we're launching a product called Ocean for Spark, which is basically the Spark platform we had built at Data Mechanics, plugged on top of their managed Kubernetes offering called Ocean. So really, it's a pleasure to be with you today. This talk is not a commercial talk. We're going to talk about something else called Delight, which is a free and cross-platform monitoring tool that we developed. So first, I'll just say a few words about Spark and data mechanics in general to set the stage, but then we're going to talk about Delight. Okay, what is the problem that we want to solve? What is the vision? How does it work in practice? And to really show you in practice, we're going to have a bit of a live demo where I'll be showing you some of the Delight screens and showing you some real customer pipelines and some insights that we can get from Delight to increase the performance of these Spark pipelines. If we have enough time at the end, I prepared a few additional slides as really a bonus, like maybe the dessert, because Spark 3.2 was released last week, and I'm kind of excited about that release. But we'll see. If we don't have enough time, I'll redirect you to a blog post that we wrote. Very high-level intro about Spark. I presume most of you will be familiar. It's the #1, distributed analytics engine. What makes Spark popular is first that there are high-level APIs in Python, Scala, and SQL, and that are make Spark pretty easy to write. Okay, and the most popular API, by the way, is definitely Python. And the second thing that makes Spark really popular is that it's very versatile. So you can use Spark to do business intelligence and interactive data exploration, machine learning and data science, to obviously data engineering, whether it's more like batch ETL workloads or whether it's real-time streaming workloads. So, Spark is easy to write. However, I would say that managing a Spark infrastructure and debugging a Spark application when there's an issue is hard. And this is why I decided to create a company to make Spark a lot more developer-friendly and more cost-effective. So these are the problems that we're trying to solve really at Data Mechanics. Make sure it's not as tedious to get started, make the platform more open, make the platform more cost-effective, leading to lower costs, and making it simpler to debug Spark applications. And Delight is a specific tool, okay, that we developed and tries to help with this pain point. Before talking about Delight, just want to talk about Spot and data mechanics at a high level. Spark can now run on top of Kubernetes. This ability started with Spark 2.4 a couple of years ago. It was officially made production ready in GA this year with Spark 3.1. And I really think it's a game changer for the Spark community, that you can finally have the same kind of developer experience and also a cost effectiveness that you have with Spark as you would have with the rest of the software engineering world. And at a very high level, our platform lets you interact with Spark either by a UI, by a REST API, by connectors to specific schedulers, like Airflow is very popular, but we support other, and obviously by running Jupyter notebooks. And then, we manage the backend, and the backend is a Kubernetes cluster in your cloud account, Amazon, GCP, Azure, that is automatically scaled, that also has some automated configuration tuning and some optimization to make Spark stable and cost effective. But again, this isn't about a commercial product. This is about Delight, and Delight is a completely free tool that you can use actually on top of any Spark platform. So you can use Delight on top of Databricks, EMR, Spark on Kubernetes open source, whatever. And obviously, if you use our platform, you get Delight natively integrated. So what was the pain point? Why did we develop something? Today, when you want to monitor what happens in Spark, mostly you will be, the only tool really that you have is the Spark UI. And this is a screenshot here of the Spark UI. I would say that there are a lot of numbers that jump at you when you open up the Spark UI, but there's a lot of noise, and you need a lot of expertise. Some people would say tribal knowledge to figure out where to focus your attention and to know what's wrong or what isn't. The second issue is that there are few system metrics. So if you want statistics about your node or your executor, memory usage, CPU usage, IO usage, usually you will use a separate tool like Ganglia or Datadog or Grafana and Prometheus. And the problem is that these tools are general purpose. They were not built for Spark. And so going from the Spark driver to different executor is not native at all. If you want to correlate the metrics that you see on this tool with your Spark code, it's very complex. Basically, you'll have to jump back and forth between the Spark UI and your tool, and you'll have to match on a certain timestamp. And the last pain point is the Spark history server itself, which is the server that can render the Spark UI after an application has run. It's kind of slow and unstable. So to solve these problems, we developed Delight. So Delight first gives you these metrics that I was talking about: memory, CPU, IO, and they're captured within Spark, and they're displayed on the same timeline as your Spark phases, so that you can correlate, the memory has increased right while I was starting that job that does a certain join or certain shuffle. Second, hopefully with our UI, we make problems obvious. If something is wrong and we can tell it from the metrics, it should show up very clearly. Oh, you have an issue with parallelism, you have a big issue with memory. And the next step is to actually give automated, actionable insights and recommendations. That's not fully implemented yet, but that's the vision. And finally, it's easy to set up. So Delight basically consists of an agent running in the Spark driver, and then the backend is fully hosted for free on our side for free. And so it's very, you can get started in a few minutes. Quick history about Delight. It started about a year ago with basically a blog post detailing our vision. In November last year, we released the MVP. And in April this year, we made it public in GA. It works, again, on top of any Spark platform. And the development doesn't stop here. I mean, actually, since April, we added a few features. And there are ambitious plans for Delight, including these automated recommendations that I mentioned. Also making Delight accessible in real time while the app is running, because today it only becomes available a couple of minutes after the app is finished. And adding new pages to the Delight UI, including a page for stage and a page for the driver. Okay, so this is the vision. Now, how does Delight work in practice? There are two pieces. There is the Spark agent, which is an open source agent running within your Spark application, within the driver. It implements an interface called Spark Listener. So it's basically a jar that you attach to the driver. And this agent will be sending some metrics to our hosted backend. I should say two important things. These metrics are encrypted. Okay, you provide a certain secret that will help encrypt them so that they only become available to you. And the metrics that we send is not data that we try to exploit. They're only visible by you. And in fact, they'll be automatically cleaned up after 30 days. And so the backend is on our side, and all you need to do is connect to delight.datamechanics.co, and you'll see the web app dashboard appear. So if you want to get started, you just create an account on delight.datamechanics.co. Once you create an account, you can create what we call a token, which is the secret that will help us identify that it's you running the app and make sure that your logs are only visible to you. And then you will install the open source agent. And here we have slightly different installation instructions based on your Spark platform. And you can find them on our GitHub page. And that's it. Then your Spark applications will start showing up on the dashboard as soon as they're completed. I wanted to give a couple of examples. So here's an example of how to install Delight on top of Databricks. One option is to configure an init script, which is basically a bash script that runs on your Databricks clusters early on. And this script, what it does is it installs, it downloads a jar, puts it on the driver, and then it inserts a couple of Spark config, including the secret token that I mentioned earlier. And if you want to install Delight on EMR, it's pretty similar. You just submit a few Spark submit options, including this package option, which will, where you provide a Maven coordinate, and this will download the Delight jar, and a couple of configs, like the secret, to encrypt your application logs. And obviously, there are similar instructions if you're running on Dataproc, if you're running on Spark on Kubernetes open source. Really, any commercial or open source platform is supported. So once you've done that and you run an application, once this application finishes, it will show up on Delight. It doesn't show up in real time. Okay, we need a couple of minutes to process the logs and make them available, though we're working on making this available in real time while the app is running. So on this dashboard, there are a few things that should kind of look familiar, like the name of your Spark application, whether it completed successfully or whether it failed, when it started, the duration, the volume of data that was read and written by the Spark app. And there should be a few columns that you might not be familiar with, like Spark task, CPU, and efficiency. These are high-level stats that will help you track your costs. Understand, am I using a lot of compute resources, and am I being efficient, or am I being wasteful? So maybe let me explain these three statistics on an example. So the CPU column is actually the total CPU uptime used by your Spark executors. Let's say that you have an app that runs for an hour and that had 3 executors with 2 cores each. Then that would represent 6 core hours of CPU uptime. So these are really your compute resources, and this metric is counter-proportional to your cloud costs. The second metric is the sum of the duration of all your Spark tasks. So if you remember, a Spark task is executed by one CPU core at a time. So here on this example, you have one CPU that maybe ran a Spark task, for a few minutes, and then that core was idle. It didn't have any work to do for a longer time. Well, maybe here the core number 3 had a Spark task to run for the entire time. And so here you can see that even though you provision maybe 6 hours of CPU resources, these cores were only used for a fraction of that time, 72 minutes in my example. And now the ratio between the two, 72 minutes divided by 6 hours, this is the efficiency ratio, 20% here. And so this is the fraction of the time that on average, your Spark executors were running Spark tasks. And so obviously, a higher efficiency is better, and actually 20% is a bit wasteful. And usually when the Spark UI looks like this, I mean, the reason is that you had one task that took a very long time to run, a straggler, maybe was processing more data because of a data skew. And so this could be a cause of a low efficiency. So maybe going back to the previous slide, here we had one app. It was called Notebook. That had a pretty poor efficiency, and we had one app called Daily ETL Pipeline that had a good efficiency. One note maybe about notebooks. On average, notebooks have a lower efficiency than programmatic apps because you interact with Spark in an interactive way, right? You run a cell, you look at the results, you edit a new code before you run the next cell. And so there are a lot of breaks where your Spark cores are not doing anything. So that could be obviously one of the reasons. Okay, so now that I've explained really the high level about how Delight works, I want to show you concretely, show you live screens of the Delight UI. And And oh yeah, before I do, because we started talking a bit about efficiency, I just want to say what are the most common causes for a low efficiency. So one common cause is the lack of dynamic allocation, meaning you have a fixed number of executors, while it will be more beneficial to have to be able to add and remove executors dynamically. This is particularly important for notebooks because you might start running a notebook and then go into a meeting for an hour, and so you'd like that the resources associated with your notebook scale down while you're away. You could be provisioning too many executors. You could be defining too little number of partition. We'll see an example like this. Or it could be, task duration skew, etc., etc. So now let's start looking at this on real world example. And so we're going to look at really customers using Delight. The United Nations UNGP program is one of them. And I want to, because you haven't seen that screen yet, so I want to use that screen to explain what's going on in Delight. So first, here you can see some high-level statistics that I mentioned earlier: how much data was read and written, duration, Spark task, CPU uptime, and efficiency. You can see that indeed Spark task is about half of CPU uptime, and so the efficiency is about 50%. And here, something pretty interesting is you can see that some Spark executors were constantly added and removed. So this is an application that was configured with dynamic allocation, probably was a notebook. And so that's why you can see that the total number of CPUs, of course, allocated to the app goes between 0 sometimes to 1 and to actually a maximum of 10 cores here. And then the app scaled down again, actually to a size of 0. So only the Spark driver was running. And then, maybe that person took a quick break. And then 15 minutes later, it ran another query. And again, we acquired executors. So again, this is really the only cost-effective way to use Spark in an interactive way. It's to configure your notebook so that it automatically scales up and down. Another thing that we can see here is the peak memory usage for each executor. Here, the peak memory usage for each executor is about 80% of the total capacity, which is pretty common and which is fine. You can also, from here, have this view over time. Let me find an interesting executor. Okay, executor 5, for example, that was used during this portion of activity. If I find it here, I'll see that the memory usage was initially somewhat low, around actually a gigabyte, and then it increased to about 2.3 gigabytes. Here, nothing bad happened, but this is an interesting screen where you can debug at which point in your application you run into an out of memory error. And so you could correlate, oh, this occurred during job 5, stage 5. And so you could dive deeper. Okay, when I click here, this opens up the Spark UI. So under the hood, we run a Spark history server. Okay, so it's still possible to open up the Spark UI from here. And you can see that, oh, okay, this application was converting a Spark data frame to pandas. And so, oops. And so this is why maybe the memory usage has increased because we were collecting some data. And this is why also it's a stage. If I zoom in, it's a stage that was entirely CPU. Okay, there wasn't any I/O going on because I was just converting my Spark data frame to a pandas data frame. Okay, so I hope this was useful. I'm just going to close this because the next demo are going to be on a slightly different environment. So we're now going to move to another customer who uses data mechanics for kind of data engineering pipelines, their weather analytics platform. And we're going to look at a different type of issue that we can troubleshoot with Delight. Here we go. So if we look here at the main statistics, we can see that the efficiency is 40%. And this is actually an ETL pipeline. And so 40% is low. I mean, it means that you're wasting more than half of your compute resources. When you look at the breakdown, you see that the reason why it's low is because, yeah, for half of the time, a portion of the cores were idle. And when we look here at the timeline, we can see that from this time, so around 2 minutes, until this time, around 9 minutes, all this gray area were Spark cores that were, you know, running. They were provisioned, but they were not actually a busy running Spark task. They were idle. And so if we want to understand, we would click at that specific stage and see what's going on and see, oh, this stage had only 2 tasks, even though based on the Delight UI, I had 16 cores provisioned. So this is bad. So here, the next step would be to look at the code and see why are there only two tasks, 2 partition? Did I repartition? Did I make a mistake in my Spark configuration? And so this is how you could, improve the efficiency of this app. Maybe forcibly increasing the number of partition before running that stage. So I hope this shows some of the value because again, this is the kind of issue that becomes really very visible, very obvious using Delight. And if you just look at the Spark UI, you really would spend a lot of time to actually realize, oh, this is what you should focus your attention on. All right, I want to move to 2 last examples. One of them is an example of a customer that was suffering from slow shuffle. And we took an action based on the feedback from Delight. So this app efficiency was good, 86%. So the Spark cores were running tasks most of the time. But when we look at the breakdown, we can see that most of the time was spent doing shuffle. And shuffle are the pretty expensive phases of your application where you exchange data across the cluster. You want to minimize shuffle. And here it was very clear that shuffle happened during stage 46 and 47. What we recommended is, so when you write a lot of data, when you shuffle a lot of data, the bottleneck can be actually the disk throughput, okay? Because you're going to be writing the data to the disk, and then you're going to be pulling the data to another executor. So a common technique when you have a lot of shuffle is to have a faster disks. And so in this case, the customer used to be running, say, EBS volumes, Elastic Block Store. And instead, we have them use an instance that had a local SSD disk. And so Spark would start using the SSD to write the shuffle data rather than the EBS. And the change was huge. Okay, we went from an app that used to run in a couple of hours to an app that now runs in 26 minutes. And the shuffle section is almost gone. Okay, so we don't spend, the bottleneck became something else. We see here, by the way, that some stage actually failed and had to be retried until they eventually succeeded. So there is still something else to improve on, but already the app went from a duration of over 2.5 hours to a duration of 26 minutes. So it's a huge savings in terms of costs. And sometimes it's not just about cost; it can be just about an application running successfully and not failing. I want to maybe show just that example. Should be very quick, just to show you some example of either running R or running Python and how it shows up in our application. I think this one, no. All right, this one was running R. And so when you look at the bottom here, you can see that obviously in the Spark executor, the JVM is using some memory, but you can also see an other. Here, other, I mean, I wish we could say R, but you have to know that you're running an R application. And so your R processes on the Spark executor are consuming some memory, and this is how you see it. And here's another application where you're also going to see the Python memory used by your executor. And here, really the benefit is to be able to know, oh, I had an out of memory error, my executor was killed, and to be able to troubleshoot. Is that because Python was taking too much memory? Okay, because that happens. And so here we can actually see that this executor at some point reached its maximum capacity, which is fishy. Probably something bad happened for that executor. Okay, we're almost at the end of my time, so I just want to say a few words to recap Delight, and to thank you also, and to tell you that if you want to try it, you can sign up at delight.datamechanics.co, install the agent, and then get started. And feel free to connect with me. I put my contact details, email, LinkedIn, Twitter, anything works, to give me your feedback, and so that we can keep making Delight better. With the 2 or 3 minutes, I said that we had a little bonus content. It's the Apache Spark 3.2 release. It was released last week. I just wanted to say really a few words at a high level. So here are some of the main features in my mind. One of them is the fact that the Koalas library is now bundled with Spark by default, so you can use it without installing anything. And Koalas turns your pandas code into Spark and makes it faster. The other thing is that Spark 3.2 comes bundled with Hadoop 3.3.1. And even if you're not running Hadoop, even if you run Spark on Kubernetes, you might be using the Hadoop libraries in particular to talk to S3, and it makes S3 much faster. So this is another great news. And it also comes equipped with RocksDB, which is used for streaming queries as a state store, and it will make streaming queries faster and also more stable. A last feature that I'm particularly excited about, because our platform only runs Spark on top of Kubernetes, and this is a Kubernetes specific feature. It's called PVC reuse. I actually have a couple of slides to go deeper into it. So PVC reuse. Since Spark 3.1, it's possible to provision persistent volume claim, basically Kubernetes volume, and mount them into the Spark executors. These are volumes that could be backed, for example, by EBS on Amazon. And these volumes are automatically cleaned up when an app finishes. So for example, you would mount that volume in an executor. And so when an executor produces shuffle files, the shuffle files will be written in that disk. Now, with Spark 3.2, the PVC will survive the death of an executor. So if an executor dies, for example, because of a spot kill or because of an out-of-memory error, the PVC associated with it lives on. And if a new executor comes in, like exec2, Spark will reuse the existing PVC and mount it there. So what is the benefit? It will speed up the creation of executor 2. And more importantly, the shuffle files which were written can be recovered by Spark. And so this is a huge game changer, okay? Before, when you had, let's say, a spot kill, you lose all your work, you have to recompute the shuffle files. Now, you just start a new executor and you recover the shuffle files. So really, we're getting closer to the goal of separating compute and storage resources in a cloud-native way on Kubernetes. And so that's a feature that we're excited about and that we're now starting to try with some of our customers. I think we're over time. So again, I want to thank you all for your interest, and I'll be moving to the conference room to do some Q&A.